So let's go back to the beginning and do some examples with logic. So we're frequently being asked whether two propositions are equivalent or whether some argument is valid. So let's do an example along those lines. Which of the following are equivalent? P if and only if Q, P if and only if not Q, not P if and only if Q, so these are in parentheses, and not P if and only if not Q. So you've got four propositions here, and we want to decide which among them are equivalent to each other. So how are we going to approach this problem? Well, let's try to remember back to doing logic, and let's try to remember what kind of tools we were using to think about questions like this. So what kind of tools do we have? We had essentially basically two different tools: truth tables and logical equivalences. Now for this situation, I don't think I can be bothered to go look at the table of logical equivalences. And I guess I didn't write this question with that in mind either. So if I went and looked at the table of logical equivalences, it might just tell me the answer right away, which is not the worst thing, but let's do this using a truth table then. Because truth tables are, one of the main tools we were using to talk about equivalence. So let's remember how those work. We start with writing down the truth values of our two basic propositions. And then we just expand our truth table. Excuse me. We expand our truth table with all of the rest of the propositions that we're interested in knowing about. And let's see how long it takes to fill this in, but let's take a start. So let's fill in this column, P if and only if Q. So remember, P if and only if Q means that P and Q have the same truth value. So it is true when they're either both true or both false. That means it's true here and here, and the rest of the time it is false. What about P if and only if not Q? This column. This is true when P and not Q have the same truth value, which is the same as saying that it's true when P and Q have opposite truth values. So like this and like this, and it's going to be false when they have the same truth value. So what did I just say? It's true in these two cases and false in these two cases. Okay, and we can actually finish this off quite quickly, because if we're thinking about it in those terms, we said P if and only if not Q is measuring whether P and Q have the opposite truth values. And not P if and only if Q is going to do exactly the same thing. So to say that P and not Q have the same truth value is the same as saying that not P and Q have the same truth value. So these should be equivalent. And if we track down, I mean, again, we're looking at the rows where they're opposite. We see that these two guys are equivalent. And we can also see already that these two guys are the negation of this guy, because you can see that each of the truth values is opposite in these two columns. So this is negation. And finally this, if you go through it, maybe I won't talk through it, but it should be equivalent to this guy. So it should be true, false, false, true. So the result is that these two are equivalent because we have written them in a truth table and they have exactly the same truth values at every step. And these two are equivalent for the same reason. And the relation between these two pairs is that they are the negation of each other. Question about logical equivalences. If you're going to prove something using logical equivalences, should you name them? And I will say you should give some idea of what you're doing. So naming them is a good way to do that. But there's also the fact that I think if I remember correctly, in the tables, they don't always have names. So let's say, if they have a name, then it's good to use it. But if they don't have a name, then don't worry about it. All right, so now how about an example with negation? This is also something that I've seen people get tripped up by. So I do have a couple of comments about this as well. Well, let's do it in terms of an example. So there's something called the Archimedean property of the real numbers. And what this means is for all real numbers, there exists a natural number such that the magnitude of a real number is no larger than this natural number. So essentially this is saying, for any real number, no matter how big, there's always an integer that's bigger than it, essentially. So before we actually go into this, I want to return to a question about this question. Can we do this by saying that the first one and the fourth one are contrapositive? So my first instinct is that that is a slightly weird thing to say, because remember that contrapositive is something that we apply to an implication in one direction. So the contrapositive of this is not Q implies not P. But you could say something that if you want to use this type of argument, P if and only if Q is equivalent to P implies Q and Q implies P. So it should also be equivalent to if you take the contrapositive of each part. because contrapositives are equivalent, these two things are equivalent, then you can substitute them in propositions to get equivalent propositions. And what you will get is not Q implies not P, and not P implies not Q. And what you can see is that this is equivalent to not P if and only if not Q. So, yeah, you can do it that way as well. But I do think I want to be precise and say that it's not that these are the contrapositives of each other. But you can use contrapositives in this sort of way to get them equivalent. Yeah, very good. Okay, this is crowding my space though, so let me erase it from the lecture notes. All right, so back to our negation example. What is the negation of this? Without using the word not at all. So first I want to give a little teaser of, this is a real thing. This is an example of a thing. And it seems quite obvious about the real numbers that for any real number, you can always find an integer that is bigger than it. But there are things besides the real numbers that are non-Archimedean. So there are, different ways of ordering numbers so that the integers do not get bigger and bigger. And so you can find things that are bigger than all integers. Strange. But, okay, let's get back to our logic. What is the negation of this? And we want to not use, we want to totally avoid using the word not. And I want to say a couple of things about this. The first is that to some extent, this is, just a requirement for this problem that I am imposing. But there's a sense also in which this is best practice if you can manage to do it when you are writing down negations of things. And that is because you want to try and write it in the clearest way possible. And writing it, writing not at the front is technically correct, but often it is much clearer if you can rewrite it in a different way. So let's do that for this. And the way I will do it, which is clear to me, so hopefully it will help you, is I find it useful to translate it into symbols and then translate it back. So let's identify this as one quantifier for all, another quantifier there exists, and then a propositional function at the end. So we write this as for all x in R exists n in n, such that I'll just write, x less than equal to n. And let's put a not at the front. So this is our negation. But now we want to try and rewrite it in a clearer way. So we will use the, I feel like this is the almost the only rule I ever use for negating things. There are, there's not a huge variety of situations. So we will use De Morgan's law for quantifiers. Yeah, in fact, if I'm trying to think of any tips and tricks about doing negations, it's really all about, the De Morgan's law for quantifiers, De Morgan's law for and or, and then how to deal with inequalities. I feel like if you know those three things, then you can pretty much nail any negation. So we will use two of those three things in this. We don't need to worry about and versus or, but we will need to worry about inequalities. So De Morgan's law, remember, tells us that we can pass the not through a quantifier if we flip the quantifier. So turn for all into there exists, and vice versa. So that was just passing it through the first one. We can then pass it through the second one as well, in the same way. So there exists X and R, such that for all n in n, not absolute value of x less than or equal to n. So let me skip those for ease of writing. So what does it mean that this inequality is not true? So remember, you need to flip the inequality, first of all, and you also need to exchange strict and non-strict inequalities, right? So you can think of that as if you have your number line, and you have some subset like this. So this is saying like x strictly less than some number. What is the negation in the sense of the, the complementary thing? It is this with the thing filled in. So this is x greater or equal to a. So to negate this thing, we should get for all x there exists x that for all n, absolute value of x is strictly greater than n. And then we don't have any space left, but let's make a little bit of space real fast. Then we can rewrite this. This last step is not strictly necessary. If you want to leave it here, that's totally fine. Because first of all, let me point out that at this point, we no longer have any uses of the word not. So let me actually, since this is a fine point to stop, let me write it out in detail. But let me also translate it back into English words. There is an x real number such that for all natural numbers, absolute value of x is greater than n. And again, just to connect this to other things, this is a thing that happens sometimes, not with the real numbers, but with other more exotic number systems. You can have situations where there are numbers that are bigger than any natural number.